Hello, Mr. Aaron, Mr. Ryan, are you alright?
Yep.
Okay, so today we're going to talk about an interesting data structure. Okay, so before we talk about a new data structure, what kind of data structure have you learned so far? Data structure, you know what's data structure? What's data structure? Come on. The thing is to hold data. So what kind of data structure in computer science have you learned so far? Come on, you have learned quite a lot, right?
Yeah.
What are those? Can you give me an example? Tree? Yes, good job. Tree is a data structure. What else? Come on, the one you usually
Stack. Queue.
way down,
Queue.
stack, queue, okay? And what else?
Heap. Heap.
Way down, heap. Yeah, we have learned talk about heap, min heap, max heap. And what else? Come on.
Set.
Way down, set. What else? The one we talked about yesterday, you know, to start with G.
DQ.
G. Q is DQ. DQ.
Graph.
Way down, graph, okay. So these are all data structure, yeah? Set or hash table, yeah? Hash table, notebook, yeah? These are all the same thing, yeah? Yeah. Set is contains unique numbers, unique elements on it. Hash table, when we talk about a table, we have this key value pairs, yeah? The time, why we need this? Because we want the constant time, O1 time, to look up the items, to check if the items exist in the table, and then it takes the O1 constant time to put it, update the entries in the table. Okay. And graph, we talk about graph. Yes, graph. This contains the vertex and then edges. It's a collection of the vertex and edges. Queue, stack. Yeah, these are quite normal. Tree, and the most important thing we have list. Yeah, a list. And list, arrays. What else? Linked list. Yeah. Linked list, yeah, linked list, yeah. We talk about several problems about linked list. Yeah, directional, singlet linked list, one directional. If it's two directional, we call it double linked list. Okay, two directional. Yeah, but these are all graphs. Yeah, you can think about the linked list as a graph as well, right? The graph, yeah, DAG, yeah. What's DAG?
Directed acyclic graph.
Yes, directed acyclic, and it could be undirected, yeah, yeah.
Dag.
It could be cyclic as well, and it could be, yeah. Okay, so tree, yeah, we call about tree, yeah. Look, yeah. If two trees, what do we call it? Come on.
Two trees.
If three trees, we call it what kind of
Three
trees?
trees.
Come on.
Forest.
Well done, wow, clever. Yeah, forest, yeah. Forest is kind of graph as well, yeah? Yeah, okay. Today we're going to introduce a new data structure, which is called disjoint set. Okay?
I thought you union.
Union file is aggregate that use the disjoint set, but
I thought you said destroy set.
okay, disjoint. What's the disjoint mean? What's this mean?
And
Disjoint.
you break up the set.
We break up the set like that. Yeah? It's like that. Okay, so sets. Okay, so interesting. This disjoint, for example, like this is number like 0, 1, 2, 3. So how many groups are there? How many groups?
4.
4. Well done. And if I tell you I want to union these two, and these two becomes a group, right? And how many groups are there?
3.
Yeah. Okay, so this is the basic data structure. So why is it useful? Remember, yeah? Remember we have these, yeah? We want to find out if there is a path between, remember a few days ago we talked about this. We want to find out if there is a path between 0 to 5, right? No, yeah, we use what kind of algorithm? We have learned two algorithms to solve this problem, to find out if there is a path between what? We have find the path exists in the graph, right? Yeah. So what kind of algorithm do we use? Come on, to traverse the graph. What kind of algorithm do we use? Breadth search, depth search, yeah. So for depth search, we find out if there's path. Yeah. For breadth search, also we expand it in the double-ended queue, and we try to exhausted all the nodes. Yeah, before we find if there's a pass, if there's a pass, we return true. Otherwise, we return false. So to solve this problem, if we can consider this graph, as different, alright. Look at the beginning, how many nodes? 0, 1, 2, 3, 4, 5. If this is 5 nodes, okay? That's 6 nodes, alright? Okay? So 0 to 1. These at the beginning, these belongs to different groups. How many groups are there?
6.
6 groups. Okay, so I found the edge 0 to 1 connected to 0 to 1. So what does it mean? If there's an edge, 0 and 1 belongs to the same group, right? Yeah? So what does it mean? I put it together. Okay, 2, 0 to 2, what does it mean? I want to put the 2 in the same group, right? Yeah? So same group. 3 to 4, same group, right? 3 to 5, same group. Is 0 and 5 belongs to the same group?
No.
They are different groups. So they are not connected. There's no path between 0 to 5. Got it? Is there a path between 0 to 2?
Yeah.
Why is that? Because they belong to the same group.
Yeah. How do you know?
Yeah?
How do you know if they're in the same group?
Yeah, that's why we use the disjoint set. I'm just talking about how to solve that problem. Remember, this one is easier, right? Yeah, it seems easier, yeah? I just, if an edge, what does the edge means? These two nodes belong to the same group. Right? And is there a path between 0 to 4?
No.
Because they are on a different group. Right?
Yeah.
So this is very useful. So to solve this problem, we need to disjoint set. At the beginning, each node is different individual group. But when we have a function to call unite, yeah? Is it a way to correctly spell the word? To merge to, or we can call it merge. Merge, yeah, better. If we merge, what does it mean? 0 to 1, and then we will update the data structure to make them make both belongs to the same group. And then we also have another function called find. Find parent. Find group, okay? Find group. So this will return a different group. Yeah, find a group of 2, right? Yeah. And we also have what? Group count. Group count. Group count. Yeah, to tell how many groups are there at the end. There are 2, right? And what else do we need? If it's a same group, yeah, belongs to same group. So this is easy. How do you implement the same group? 2 numbers, A and B. You just need to check if the group is the same. Find group A equals to find group B, right? If they are same group, they belongs to group number, okay? So what's group? So at the beginning, okay, so that's easy. Look, how can we do this? Okay, so first of all, we have a parent, okay? Parent. Class, let's define it. Class, disjoint set, okay? Let's call it disjoint set. Disjoint set. Okay, so at the beginning, we want to have a constructor. Remember how to construct in it initial, and we're given an n. N is the number of the at the beginning, the initial group number. Okay, if there's a 0, 1, 1, 2, 3, 4, 5, so we just pass what? 6. Okay, then you from 0 to 5. So there's a self. Then we can construct self the parent. Parent equals list range n. Okay. So at the beginning, if n given a 6, okay, 6. So the parent is a list of 0, 1, 2, 3, 4, 5. Okay? So what does it mean? At the beginning, 0, 1, 2, 3, 4, 5. These 6 groups, there are 6 groups, and the number is the group ID, right? Okay, yeah? So how can we make, if I want to make merge 1 and 2, so what does it mean? I need to change, right? If I want to look 1 and 2, if I want to merge these two, what happens? So I just need to change this value to 1, right? Yeah. then these two belongs to the same group. If I want to merge 1, 3, and 5, I can change 3 to 5 or 5 to 3, right? Yeah, got it? This is called a merge. Yeah, just to change just change the parent value of one node to a value. That's the group ID. And initially there are 6 groups. There are group ID. These are group ID 0, 1, 2, 3, 4, 5. Okay, okay. So now save the parent. And then we need to find. Remember, we need to find what? Same group. Okay, that's same group. Same group. Given two numbers A, B, how can we find if they're same group? How can we find if they're same group? Return what? Return what? Save the parent. Tell me, save the parent. If they are same group, what happens? Save the parent A and save the parent B. What happens? What if they're same group? What are those? I mean, if they're same group, how can we find the same group? It should be, I mean, okay. So there's something missing here. Okay, so look, 0, 1, 2, right? So if the same group at the beginning, we need to have a function to find the parent of it, right? To find the parent of it. So how can we find the parent of it? I leave this empty for now. So how can we find the parent? We need to have this find parent. Find parent function. Okay, x. Let's find x. Okay, so what does it mean? What does it mean? Look, Eric. Look. If at the beginning this is 0, and then 0 will be point to itself, yeah. And then if we merge 1 to it, 1 could be merged here. If we have another 2, merge it to it, yeah. 3, yeah. So look, if 3 parents, if 3 belongs to the group of 2, 2 also belongs to group of 1. So these are all connected, right? But how can I make sure this? I want to get the value of 0, the group 0, because all these 3 belongs to 2, 2 belongs to 1, 1 belongs to 0. It could be, there could be a link, right? So I need to find out the parent of the x. So how can I say? If x not equals, save the parent. Okay, save the parent x. If x equals save the parent x, what does it mean? If at the beginning, look, x equals save parent x, then this is the group, this is the parent of it, right? Does it make sense, Eric? Yeah, does it make sense? Any
Allyhoos.
Yeah. Okay. Look, Eric. Here is a look. If 0, right? This is a group ID. If at last, right? Change here 0. I want to find the group of the parent of the group of 0. Group of 0 is equals 0, and then you return here, right? If this is 0, and I want to find the group of it, apparently it's not equal, right? So what does it equal? What does it equal? Look, x is 1, right? x1 is not equals to 0, right? Yeah? Say parent x is 1. It's not equals to 1. So what happened? What's this? It should be 0, right? So I need to do what? I need to return what? Find parent. Find parent what? Save the parent x. Yeah? Yeah? I just call it save. Look, save the parent x. Save the parent x is 0. Yeah? Because look, current is 1. 1. And then 1 is the same group as 0. So I want to find out the zeros group. So I need to put this here. So it recursively call itself, right? Got it? So that's what he here says. Look, 0. If here is 1, right? The second 2 is the same group as 0. And then 2 is the same group as 1. Right? I want to find out the 2. The group of 2 here. I mean, look, I want to find out the group ID of this one. I need to find out, in order to find out the group of these, I need to find out the group of these. In order to find out the group of 1, I need to find out the group of 0. until what? Until the group of Excel equals the zero value equals the group of it, the parent of it, right? Yeah, got it? Got it? Yeah, so that's why it says 3 points to 2, 2 points to 1, 1 to 0. So, look, in the worst case, right? In the worst case, what's the time complexity of looking up the parent of the of the element? Yeah, in the worst case, over. Oh, and right now, look, if there are 10, 0, look, it could be, yeah? Look, if all these are connected, what happens? If I want to find a group of 4, it says, okay, the group of 4 is the same as group of 3. Okay? The group of 3 is same as group of 2. 2 is same to 1, 1 is same to 0. Right? I need to follow the path, right? Yeah? Is there a way to make it, better? Because I don't want to query so many. So in order to do this, I need to compress the path. Compress the path. So what is it? It's the same as what? 0, 1, 2, 3, 4. Right? Which one is more efficient in querying? This one. Why is that? Because at most 1. Yeah. For example, I can't query 4. Here 0. 0 points to the cell, right? Yeah. This is the root, right? The group root is like the tree. Right? Eric, got it? Right, and don't mess up with my computer. Okay, got it? So how can we do this? How can we compress the trees, the path? We just have to do one thing here. Look, we just have to do one thing here, Eric. In order to compress the path, when we look it up, Eric, when we look it up, look, listen, otherwise I cannot continue. When we look it up here, we want to point it out to 4 to the 0, right? Everything I query up, when I query up the tree, the path, I want to repoint the parents, the group ID to the root, right? Okay, got it? So in order to do this, we just have to do here. We just have to do this, what? Parent, self the parent, yeah? So parent x equals what? Equals 5 parent. 5 parent. 5 parent. What? 5 parents. Parent x. Parent x. And then return. Return what? Return what?
Return.
Return self to parent x. Yeah.
Self.parent x. Yeah.
Look.
Oh,
Parent x is this current list node. I want to point to the root, and then this root is recursively obtained from parent x, 5 parent dot parent dot x, and then I finally return self dot parent x. Okay. Okay. So what happened here? Look, 4 points to 3, 3 points to 2, 2 points to 1, 1 points to 0. Yeah. When I
0
query.
points to 4.
No. Look, when I query parent 4. Okay, what it does is what? Parent 4, I want to point to parent of 3 here. Which is parent 2, parent 1, and parent 0. So eventually this function will return parent 0. So I will repoint here, I remove this. And I will repoint here, I remove this. I will repoint here. Yeah, so eventually it will become 0, 1, 2, 3, 4. This is to call compress the path, yeah? So that will reduce that will improve the complexity of the finding the path, 5 parents from O(n) roughly to O1 constant time, okay? Yeah? Yeah? When we query this, we compress the path. And this could be done using interactively, okay? Not recursion. How can we do this? Okay, I rewrite it, okay. Define 5 parent. First of all, we want to find the parent of x, yeah? So how can we do this? We want to follow up, yeah? So we have this parent x equals x. Why px not equals to x? What? Px equals parent Okay, parent is set parent x. So now px not equals x, px equals parent x. What's this mean? What's this mean? What's this mean? 3 points to 2 points to 1 points to 0. What does it mean? If x is 3, what's the value of px? Eric, what's the value of px? What's the value of px?
It is.
Yeah? Yeah? Alright, look. Px is x is 3. Why px not equals x? Px is not equals 3. Yeah? Okay, so that's the problem. Px equals x. Why px not equals self to parent? Okay, so here is there's a mistake. Okay, why not equals self to parent x? So because look, if px equals parent x, what does it mean? If a value x equals parent x, then x is the group, right? It's the root, right? Why is not the root? Why this is not the root? I go up until I reach the root, which is 0, is pointing itself, right? Look, Eric. So eventually this px will be number 0. Alright. Are you lost?
No.
Okay, so what's the value of px?
The parent x.
Yeah, I know, but when x is 3, so what's the px after this loop? Px not equals parent x. Parent x is what? What's parent x?
Parent x is where that's.
2. Yeah?
Yeah.
2 is not equals to parent x. Go here. 0 is the parent x. So what's the value of px?
It is 1.
0. Come on. Yeah. I want to find a group. Yeah.
That looks like a fat potato.
Yeah. So why x not equals to px? Why x is not equals to px? I want to compress the root. Yeah. So first of all, I need to do what? I need to do what? I need to have a value to save. Like value equals. I want to save the value. Yeah. Why? Save the parent x. Parent x. I want to. This is the parent x value, and then I have parent x. Parent x. I want to save to px, right? And then what? X will be v equals to v, right? Yeah. And then finally, I want to return the root. Which one is the root? Which value is the root? Come on. Which one is the root? We're trying to find out where.
Parent.
Px, yes, px. So here is that when we are not reaching the, when we're following this, we point. This is to compress the path. Parent x, I want to point to the px here. Yeah, this is what I mean, and like x will go to the v, which is parent x. Okay, so this is the recursion version of the previous one. Okay, so once we have this parent, find parent. Yeah, alright. We talk about find parent, and how can we talk about check if the same group? Come on, same group. How can we check the same group? A and B. How do we check if A and B belongs to the same group? Can you explain to me? Not the coding. Can you explain to me how do we check if A and B belongs to the same group? Using which function?
We just look up.
Yeah, which function we talk?
Look up.
What? Can you be more specific? Which same group? What function have we talked about 1 minute ago?
Ow.
Find what?
Find parent.
Okay, so if we find the parent, if the find parent value of A and B is the same, is it belongs to the same group? Have we? Yeah. So look, we can just do this. Return find parent A and find parent B. So what should I put here? What should I put here?
Column.
Find parent A and find parent B. They have to do what? If they're same group. Ryan, any question? A and B belongs to the same group. What does it mean?
It means
Find
that A
parent.
and B belong to the same group.
Find
24
parent
minutes.
and find parent B. What they have to be equal or not?
Return
They have to be equal or not?
Yeah.
Yes. 5 parent A needs to be equals to 5 parent B in order to be in the same group. Am I right? That makes sense, right?
Yeah.
Yeah. Okay. So we have the same group, and what? Now we talk about this merge. Okay. How can we merge it?
By the.
Yeah. Okay. That's fine. Merge A and B. We want to merge that.
Yeah.
Can you not do it? Can you not do it? Otherwise, we have to do it again. Okay.
Well, yeah. So we've done it for like half an hour.
Yeah. That's fine. Merge A and B. How can we merge A and B? I and B.
Taking for a long time.
Yeah, 0, 1, 2, 3. I want to merge. Remember, I talked about this before. I just have to assign one to another, right?
Yeah.
So in the best cases, if there are two, first of all, I have to check. Yeah, I have to check what the group A. Group A equals 5 parent. Yeah, 5 parent A. Group B equals 5 parent B. If group A equals group B, what does it mean? They're already in the same group. Do I need to do anything else?
No.
No, I just pretend, right? Yeah. Otherwise, I can do what? I can do what? Parent, right? Parent A equals B, right? It equals what? Equals 5 parent B. No, actually it's group B. Okay, we already have this group B. Or we can do this. Parent B equals what? Parent A equals group B, or parent what? Or what? Or what?
Parent.
Or parent B
B or-
equals group what? Come on, we can do one of these. One of these. Yeah.
That's no group. That's.
One of these. Parent A, I can set it to group B. Or parent B, I can set it to group what?
A.
A, well done, yeah. So yeah, it's the same, yeah?
Said A.
Yeah, it's the same thing, yeah? But we want to improve this. Why? Because look, which one is better? If they are already too many, if they are, look, okay, just imagine if this is a minion group, and a group has a minion node, right? Yeah? And there's a group of just 2 nodes, okay? Yeah? And I want to merge these 2 nodes, 2 groups. I want to merge the 2 groups. Which one is better? Moving this. Which one is better, Eric? Come on, think about it. This is a question. You ready? Okay. I have a group A has a minion nodes. I have a group B which is just 2 nodes. I want to merge these 2 groups. So should I set these, the parent of these, the root at the beginning is pointer is should I set these to these? This is one way. Merge the B to A. Or should I set these, this is the root to the root of it? Which one is better?
B to A.
B to A. And you?
I don't care.
You don't care. Okay. B to
I
A
don't mind.
is the actually, yeah, this is any of these is okay, but it's better to make B to A. Yeah? Yeah, B to A.
I said I don't mind.
Yeah, okay, but I explain why merging the B to A is better. Can you tell me why merging the B to A is better?
Because you have less.
You have less, yeah. We want to merge the group of less size to the bigger size, because in this case we are not increasing the overall path, right? If we move these to here, what happens to all these paths? That these will be one more, right? Got it? Because I have a minion nodes and it affects a minion paths, right? These nodes will be affected when I query these nodes will be affected. Remember, yeah, I want to shorten the path. Yeah, I want to compress this path, right? But when this merging the bigger set to the smaller set, what happened? All these nodes will be affected. If I move this the smaller set to this, all these majority of the paths will not be affected, only affected the less. Okay. So in order to do this, we can have these sizes. Okay, we can have size at the beginning equals 1 times n, right? We have a size of each group, right? We have size of each group, and when we merge it, first of all we check the size. Which size is smaller, right? Which size bigger? We can compare this. If size A is smaller than if size B, then we merge the B A to B. Otherwise, we merge the B to A, right? Okay, I'm not going to write it, but you understand this problem, right? We want to merge the smaller size to the bigger size, and then we updated the size. Size X size group A plus equals size group B, or size group B plus equals size A. In this case, we always merging the set with smaller size into the bigger one. Okay, so when we merge the size, when we merge the group, what happened to the group count? All right, okay, it's almost going to be complete. Okay, so look, 0, 1, 2, 3. There are 4 groups. Okay, yeah. If I merge 2 groups, how many groups are there?
3.
If I merge one group, another group, what happened to the group count? Every time I merge 2 individual components, what happened to the group count, total groups?
-2.
-2? Now there are 4 groups. I merge these 2. How many groups?
3.
Yeah. So why you say -2?
-1.
-1. Okay. So I can have
2.
Yeah. I can have a connected count. Every time I merge it, in the merge function, if they are not belonging to the same group, I merge it. I merge it. So what happened to the group count? I can set the group count -1, right? I can set the group count -1, and then I can have a function. I can have a function to return the number of groups. Okay, so this is the another function. Okay, I think this is okay. So how many functions for the disjoint set? Can you remember? You don't need to don't need to remember the implementation details for now. But tell me, what kind of function do we need? Disjoint set. Come on. Find parent. I give you an example. Find parent of element x.
Return. Answer.
Find parent, and what else? Come on. How many methods do we have to talk about? Find parent and
disjoint.
Merge. Yeah. We want to merge 2. Yeah. Merge x and y. And what else? What else? We want to find out if they belongs to. Come on. They belongs to what? Same group. Belongs to same group. Okay. Same group. And what else?
2.
And we want to find out the number of what?
No.
The number of.
No.
No. Number of what? What happened to if we merge 2 groups?
We'll do this more than one.
No. Find parent. In the find parent we talk about the complex. Yeah, you know this. When we merge the group, we talk about merge the smaller one to the bigger one. Yeah. Same group. Just calling the find parent to find out if the find parent x is the same as find parent y. But if I want to know how many groups are there, right? Number of groups. Yeah. Number of groups? How can we implement this? We just keep a counter and the number of groups. Yeah. At the beginning, there are n groups. Yeah. At the beginning, if there are n groups, every time we merge 2 things, if they don't belong to the same group, what happens? We minus equals 1. Yeah. Got it? We minus equals 1, right? Okay. Okay, so we talk about the disjoint set. Okay, let's go back to that original problem. Okay, and that's it. A graph. A graph. Look. Okay.
So, yeah.
The graph. The edges. We want to find out if there's a path from start to end. Okay. Define. Path exists. Remember? Path exists, and there's the edges. Okay, look. First of all, I have a disjoint set. Okay, let's say du disjoint set ds equals disjoint set.
Ow.
Disjoint set, and there are n edges, yeah. N equals length edges or whatever, yeah. Okay, now for star n in edges. So what happened here? I have a start. Remember at the beginning I talked about 0 to 1. There's an edge between 0 to 1. What happened? What should I do with this? What should I do considering the edges? Okay? At the beginning, there are n edges, n nodes. And I found out if there are edge between 0 to 1. What happened? ds dot what? Which function we going to make these two? Come on, we talk about a few functions. What? We want to put two merge. Yes, merge what? S and E. Right? We merge two nodes. This is S, this E. And we want to find out if there there's a star. There's a 2, yeah. 2. Okay. So now we just need to find out if there are paths between star to 2. So which function? ds dot what? ds dot what?
Disjoint.
ds dot what?
Merge.
We want to find out if there's a path between star to 2. So for this disjoint set, what function should we call to find out if there are two elements belongs to same group, right?
Yeah.
So this is just same group. Star n, yeah. You see? So this one is look. No, wait. So remember before we used the depth first search, breadth first search, but with the disjoint set, look how simple it is. Yeah? The implementation is simple, right? Am I right?
36.
Yeah? Do you understand?
37.
That's okay. What's the time complexity of the disjoint set normally? Which function? Yeah, which function? Yeah. The find in the worst case, if you're not compressing the path, to find the parent takes O(n), right? But usually, if you compress the path, in practical uses, it's not just O(1) constant, right? And then merge is simple O(1), right? We just assign one to another, right? Because it fundamentally calls the find parents, and then what? Check the same group, yeah? Just calling the find parents, and what else? Nothing, yeah? Nothing. Okay, so this is O(n), okay? The time space complexity is also O(n) because there are n edges, n nodes, and n groups, yeah? We need a disjoint set to store the, we have a list to store the number of the groups for each node, right? Got it? Okay, that's it for today. Good job.